Welcome to the Alameda video tutorial about concentrating solar power. This is video tutorial unit number 7, block 5. I'm going to talk about yield analysis with Greenius. My name is Jürgen Dersch and I'm owning a diploma in mechanical engineering and a PhD in mechanical engineering. I have more than 13 years of working experience as scientist and project manager at DLR, particularly in the CSP field. My main tasks are design and programming of CSP performance models, integration of CSP and fossil-fired power plants, design and layout of solar fields, feasibility studies, and, of course, the development and maintenance of the software tool Greenius. My presentation may be divided into these sections. First, I will give an introduction to the Greenius software itself. After that, I go to general usage and the options of Greenius, and I will run through an example project, particular parabolic trough CSP plant. And I will also talk about the implementation of solar tower plants in Greenius. The software tool Greenius has been developed at DLR for several years. It's made for the simulation of different renewable energy systems. On the right-hand side, you may see a screenshot about all the technologies which are implemented in Greenius. Greenius is customized for fast and simple calculations. It is based on hourly performance simulation of a typical year, and it was initially focused on the renewable electricity generation. And the main focus was on concentrating solar power. The Greenius is utilized for feasibility studies or also for technology comparisons. It is internally used at DLR and also given to external partners in joint projects. And the recent extension we have made was to implement the simulation of solar towers. So Greenius offers a combination of fast technical performance calculations and economical calculations. It offers user interfaces for parameter manipulation and analysis of the results. You may integrate third-party methodological data and performance maps generated with other software tools. Greenius does not offer a detailed calculation of heat balance diagrams for power blocks, does also not offer design of plant piping and plant hydraulics, and is also not an up-to-date database for installation costs. If you want to start a simulation within Greenius, you have to do some preliminary consideration. First, you have to know something about the site. That's the longitude, latitude, and altitude. Then you must have an idea about the size of your power plant. That means the rated power output. You need to have a meteorological dataset for a typical year with hourly resolution. And you must know what kind of technology you want to simulate. But Greenius may also be used to compare different technologies and/or different sites. I will now give the presentation about a typical project in Greenius. That's the simulation of a parabolic trough CSP plant. If you start the software Greenius, you will see a screenshot similar to this one. It's the main window of Greenius, which is divided into several tabs: the project summary, project site, technology, economics, and results tab. And these single tabs are further divided into user interfaces. Here on the project site tab, you may see the nation, the location, load curve, and meteorological user interface. All of these user interfaces may be opened by just pushing the edit button, or predefined datasets may be loaded with the load button. If we have a closer look into the nation and the location input window, you may see that the nation input window contains a lot of information about the nation itself or the area where the solar plant has to be located. This example, it's Spain. So here are input data about the remuneration tariffs for electricity, maybe for heat, and also if there is a certain fossil fuel percentage allowed. Furthermore, information given here are financial information about taxes, discount rates, escalation rates, and so on. On the right-hand side is a screenshot of the location window where the site for the CSP plant is defined. Main input data here are latitude, longitude, and altitude, as well as time zone, and also important for the economic calculation, specific land costs. Ground structure, roughness are not so important for CSP plants, but rather for wind energy plants. If you open the meteorological data window, you have first to load a typical dataset. Such a dataset is made of typically 8,760 lines, one line for each hour of the year, and it contains information about ambient temperature, ambient pressure, ambient humidity, global horizontal irradiance, direct normal irradiance, of course, wind velocity and wind direction, if you have a full dataset. This input window can be used to analyze the data further and to generate plots of the data, look at single dates, and so on. The next important tab for the software usage is the Technology tab. Here you define how your power plant looks like, how it is made of collectors, which kind of storage is used, and which kind of power block is used. The first input window here is the collector assembly window, where the technical parameters of your collector, that means the single unit with one drive, typically about 100 or 150 meters in length, looks like. Also given here, beside the dimensions of the collector, also the nominal optical efficiency is given here, as well as heat loss coefficients and incident angle modifier equation coefficients. This slide gives an overview about the equations used for the simulation in Greenius. This is just the main equation for the parabolic draft collector efficiency. And here it's shown how these coefficients from the collector input window are used in this efficiency equation. This is the optical efficiency. Here, B0 to B4 are the coefficients for the heat loss equation, and A1 to A3 are coefficients for the incidence angle modifier equation. Greenius is using one single temperature difference for the whole solar field, which is calculated from the arithmetic mean between inlet and outlet temperature. All these parameters are of course specific for a certain draft type and must be determined by measurements. The next input window for the technology is the input window for the collector field. This again is divided into two separate tabs. One is called field data, the second one is called field operation. In the field data window, it's specified how many collectors are used in series to build up a row or a loop, and then how many of rows or loops are in the solar field. Also, the header length, header diameters, piping length, and piping diameters can be defined here. Furthermore, the distance between rows and the distance between collectors. And tracking axis tilt angle, if any, also the tracking axis azimuth angle, if the draft is not oriented in north-south direction. Greenius offers also an automatic calculation of pipe length, but this automatic calculation of pipe length is only valid and gives only typical values if the solar field is arranged in a certain manner. I'm just talking about that on the next slide. The field operation tab defines the operation limits of the solar field, or also the nominal operation temperatures. That means solar field nominal outlet temperature, nominal inlet temperature, as well as mirror cleanliness and the shutdown wind speed. Also the heat transfer fluid is defined here, and here again user may choose an automatic calculation of the fluid mass based on the volumes calculated from the left hand side. This slide will show you something about the typical arrangement which is assumed for the piping and header length calculation in Greenius. If you look on the left-hand side, there we have the typical arrangement of a couple of collectors, here 6 single collectors in series to build up a row, and these rows are collected to headers to transport the HTF to the power block and back from the power block to the solar field. Many of these rows or loops are connected in parallel to build up the whole solar field. Greenius assumes that the solar field has this typical age arrangement shown on the right-hand side, which is defined by the way the headers are arranged. If you look at these cold and hot headers, which are shown in blue and red, they are looking like the letter H. If the solar field is arranged in a much different manner, the automatic calculation of pipe lengths in Greenius would be meaningless and the numbers cannot be used. So users are responsible to give the piping and header lengths in this case by themselves. The next input for the definition of the technology is the thermal storage window. Here the most important inputs are net capacity of the storage in kilowatt hours, the maximum charging rate and maximum discharging rate, as well as relative losses in 24 hours. Also important in this window are the pumping parasitics, which are needed to operate the storage. The power block itself is similar to the meteorological data input. It has to be loaded and it consists typically of a pre-calculated performance map. This performance map has been calculated with another tool, typically a tool for thermodynamic cycle simulation, and Greenius is just loading this performance map and using it for simulation. Greenius itself comes with a couple of pre-calculated power block performance maps. They may be used and they may also be scaled. On the right-hand side, we see some scaling factors. So this is a typical power block for 50 megawatt parabolic draft plant with wet cooling tower. If you, for example, are looking for a 60 megawatt plant, in case of 50 megawatt, you can use this scaling factor to adapt this power block file to your needs. The next input tab is that for economics. Here, the cost assumptions are used as input data, the timing for the project, and the financing input data is given. If you have a closer look into the costs input window, we see that the costs are subdivided into 3 or 4 main components. First one are costs for non-conventional components. That means the whole solar field, HDF area, and so on. The second one is for conventional components. In this case, this means the power block and the balance of plant. The third input data is the storage, and the fourth one is the land cost, which has been explained before on the nations data. So Greenius uses specific costs. That means in this case, if you look for the cost of the solar field, specific costs are defined in euro per square meter of aperture. This specific value with the solar field size gives the total costs of the solar field. Furthermore, some additional costs are defined here as percentage of the sum of investment costs. These are costs for project development, insurance, supervision and startup, as well as contingencies. I have to mention that all specific costs given in Greenius are just estimates and may considerably differ from project to project. The further definition or input data for economics are for the timing. The first operation year may be defined, the operation period and the construction period, as well as the share of costs within this construction period. Financing can be defined by given percentages of different sources of financing, grant funding, debt funding, equity funding, and for the debt funding, several different lenders can be defined with different debt terms, interest rates, and so on. Once all these things have been defined or just left at the default values given by Greenius, you may start the simulation of the typical operation year. The normal calculation needs only a couple of 2 or 3 seconds to simulate a whole year, and after that you get the results and you can inspect them in the results window. The results are given on the one hand side as data table, similar to an Excel format, subdivided for hours, days, weeks and months. And the first 3 lines contain the information about the average value and the sum for the whole year. So many columns are given here, many different output data explained on the left-hand side. And there is 1 row for each hour of the year if you go into this table, this hourly table. Furthermore, Greenius may be used to inspect this information or these results on a graphical output interface. You may just choose some of this output data. In this example, 3 examples are used. The net electrical output in red, the solar heat used to produce steam in green, and D-ion collector area in orange. The resolution here shown is a daily resolution. That means these values are plotted as daily sums for each day of the year. And this figure gives a good impression about the annual impact of the DNI variation on the power plant. By using the economical capabilities of Greenius, also a detailed cash flow analysis can be done. And the cash flow output window gives detailed information about revenues, costs, operation costs, capital costs, and so on. Furthermore, the key results are shown in a special output window. It's just a summary of the most important input and output data. So here the meteorological data, the site position and orientation, the solar field dimension, and then some selected simulation results. The same is valid for key financial results, again financial input parameters, simulation results, and calculated levelized electricity costs and so on. So to summarize these information, you can say Greenius offers some additional useful features. Some of these are the plotting capabilities for graphical result analysis. The generated result files may also be exported and saved in a Microsoft Excel format for further processing. All the parameters in Greenius have reasonable results for default, and the user may save individual datasets as well as whole projects in ASCII format. Greenius is also capable to open several projects in parallel to compare results. If you're going to talk about linear Fresnel collectors, then they are, from the Greenius perspective, considered as a special case of draft collectors. So this special collector type must be loaded or generated, and the input data in the collector field form must be adapted. For linear Fresnel collectors, the incidence angle modifier is typically given as sorted table instead of polynomial approximation. And also important, the specific cost for this type must be adapted, since it's typically cheaper per square meter than a parabolic draft. This is a screenshot of the collector assembly input window for a linear Fresnel collector. It is quite similar to the parabolic draft, just the collector type is changed here and the incidence angle modifier is not given as equation but as by tabulated values. And these values are shown on the right hand side. I will now talk about the simulation of solar towers in Greenius. If you're going to talk about solar towers, they are a little bit different compared to parabolic drafts, since we have typically heliostat solar field, which is individually designed for a certain site and maybe look quite different depending on the site, heliostat size, technology, and so on. We are also using a modular approach, so one model for the power block, one model for the storage. These both are very similar to those for parabolic drafts. Then we have a model for the receiver and the tower field. And the solar tower field, in this case, is defined by a couple of pre-calculated and pre-optimized heliostat fields. For the solar tower field input window, the user has to define intercept power and design DNI, as well as tower height and design time, and as also the mean mirror reflectivity. All the other field parameters are coming from the pre-calculated performance map. For the receiver, user can define also the design intercept heat, flux density, maximum flux factor, design outlet temperature, and of course fluid type. The thermal storage and the power block, as I told before, are very similar to that from parabolic draft power plants. There is no real difference. For the solar tower power plants, Greenius is using pre-calculated lookup tables for the heliostat field, for the receiver, and for the power block. This has a disadvantage that the simulations are restricted to the table boundary values, but it has also a couple of advantages. We have a very fast simulation of the typical year, and the user needs only limited information about the system to start the simulation. And to give it again more flexibility, users may add their own performance tables if they have generated them. The pre-calculated performance maps for solar tower systems have several degrees of freedom. The first one is the site latitude. Users may choose sites between 20 and 40 degrees. The design intercept power at the receiver is limited between 10 and 640 megajoules per second. And the tower height is a mean value, but the users may vary this value within a plus minus 30% margin. Other input data or the design data are fixed. First one is the design date and time. It's always the 21st of March and solar noon. Also the heliostat mirror area and shape is fixed for these pre-calculated performance maps. We have assumed that the heliostats are rectangular and the area of single heliostat is proportional to the intercept power. with a maximum of 200 square meters for the largest system of 640 megajoules per second. The heliostat arrangement in the field is optimized. The receiver dimensions, orientation and shape are also optimized. We are using the software tool HFLCal to optimize these solar fields. And the aimpoint strategy is also fixed, so each heliostat aims into the middle of the projected area it views. In total, 36 individual HFLCal runs were used to generate the solar tower field lookup table for Greenius. These figures show some of the results contained in this lookup table. From the left to the right, the intercept power increases. We start with a 10 megawatt intercept power, an aperture area of about 16,824 square meters, equivalent to approximately 2.5 megawatt electricity output. And on the right-hand side, we have a much larger solar field with an aperture area of about 1.2 million square meters and approximately 170 megawatt electrical output. Tower height increases as well as the shape of the solar field. So the tower is always located at position 0, 0. That means we start from a north field on the left-hand side and go to a surround field on the right-hand side. The Greenius lookup table contains also solar fields optimized for different latitudes. And in this figure, the impact of the latitude on the solar field shape and the position of the heliostats are shown. The blue dots show an optimized solar field for 20-degree latitude and the red ones for a 40-degree latitude. The intercept power of both solar fields is the same. So if we go farther away from the equator, the solar field, the heliostat field, evolves from a surround field to the direction of a north-oriented field. This is a typical output for such a solar tower power plant. We have here a plot for 4 days in April. 3 of them were with fairly good DNI, and the 4th one is with intermediate irradiation. The blue line shows DNI times aperture. That means the maximum energy such a system could produce without any losses. The solar field output, in this case heliostat field output, is the green line, and the intercept power is the red line. This is actually lower than the green line, particularly for hours with very high irradiation. In these hours, some parts of the heliostat field have to be defocused in order to avoid overheating of the receiver. We can also see the storage charging and discharging and the electrical gross output, which is shown in purple. I have talked before about the possibility to use Greenius to compare different technologies. So this is one example one can do with the results. Here, the heat output of the plant of a solar field for a tower field in blue and a parabolic trough field, which is south-north oriented, is shown. Both plants have a size of 50 megawatt electric, 7.5 hours storage. They have, of course, different aperture areas, and both are located in southern Spain. The bars here show the sum of heat output of each plant for the whole year. What is evident from this figure is that the trough field with the south-north oriented parabolic troughs shows much more annual or seasonal dependency of the output compared to the tower field. You may also realize that the solar tower produces more heat and electricity in summer than in winter, but the difference between the winter months and the summer months for the tower field is lower than for the parabolic trough field. Summarize my presentation, I've been talking about the capabilities and the typical utilization of Greenius. The emphasis of this lesson was on CSP plants, and the following unit will be used to make you familiar with Greenius by performing several exercises. And these following exercises are concurrently also lessons about CSP itself. A demonstration version of Greenius and also the user manual are available from this web address, and we are going to prepare an updated free version without any restriction, which will be published soon. I would also like to thank the main developers of Greenius, particularly Volker Kwasniak, who started the Greenius development during his time at DLR, Winfried Ortmanns and Rainer Kistner, and many others who have contributed to improve the software. I would also like to thank you for your attention.